Okay, so the beginning review starting at question 6. Again, like yesterday, I'm going to pick and choose. So now our function that we're given is a rational function. And it says determine the simplified form of each of the following and state non-permissible values. So we're going to do G together. Okay, sorry, C together. It is function G. So that means everywhere there's an x, we're going to substitute 2 over x. So 2 over x plus 3 times 2 over x minus 5. So really when we do this, we get what's called a complex fraction. Fractions within a fraction. So my recommendation is, well, I guess you could go simplify anything that you can. So that would be 6 over x minus 5. And what I would do here, yes, you could find a common denominator in the numerator, in the denominator, and the divide. What you can do is remember what you do for fractions. An equivalent fraction is found by multiplying or dividing both the numerator and denominator by the same thing. So here, if I look at what the common denominator is, in all fractions in there, it's x, right? Because those are the same. So if I multiply both the numerator and denominator by x and distribute that, then I'm going to get rid of the fractions within a fraction. So 2 over x times x is 2. 3 times x is 3x. 6 over x times x is 6 minus 5x. Okay? Then you look, it's a rational expression. Can you factor anything and divide out anything? You can't. So that's your final answer. Now you may put the x terms first. So I would accept that, but you could go, okay, 3x plus 2. You could factor out, we never like having a negative as the first term in a bracket. So I could factor out a negative and have 5x minus 6. Saying that, never like to have a negative in the denominator. So I would actually, if I'm going to do it this way, show it like that, negative out front. Okay? But really, I'm going to accept this. Now, non-permissible values. You want to think about the non-permissibles from the beginning and the end, okay, for any rationals. So here, right at the beginning, x can't be 0, okay, because that alone, if x was 0 to start here, what would you substitute in? It's an undefined value. So we have to look at that bracket, what's inside the bracket, what you're substituting in. And then, of course, at the end here, you might look there. If you factored, it's a little bit easier. Whatever makes this 0. So x cannot be 6 over 5. So there's 2 non-permissible values, or 2 restrictions. Okay, and you can list them. So here, if I didn't show that up top, I might just show it like that. Okay. All right. Now, so hopefully you had done 6. Now we're going to go on to 7, which I didn't ask you to do. Maybe you looked ahead. Take a look. It says equations of functions can be written either in terms of f of x or in terms of x. So what's the difference? So in terms of x, what does that mean? It's when the function is easily defined by type, such as a linear, quadratic, exponential, all those functions we've learned and reviewed. And the function can be graphed using the graphing calculator. Basically, it's the definition of that function. Okay? F of x means you need to know what the function is to start. You can't put in y equals f of x in your calculator, right? You have to know what f of x is. So when it says write in terms of f of x, that's when the type of function is unknown, or knowing the equation is not important. Can't be graphing it, because you don't know what it is. And so really it's in function notation, f of x. It could be g of x, it could be h of x, whatever letter. It's the name of it. It's not the actual function. So it says circle the equations that are written in terms of x and name the type of function. That's the hint. It's in terms of x, you can name it. Is it quadratic? Is it exponential? So here, the first one, that is quadratic. So that is in terms of x. That's a lot. We did so much with those in Math 20. This one, it's 2f of x plus 3. Well, it might kind of look linear, but it's not, because I don't know what f of x is. So I'm not circling that. Okay? This one, though, 2x plus 1, that's linear. Now this is the name of a function, so that's the same as y equals. So we've got function notation in it, but that's the definition. So that's okay. That's linear. I can put that in my calculator and graph it. Next one, f of 3x plus 6. Don't know what the f is, right? So can't. Now again, definition, f of x equals 4 to the x. Yeah, that's an exponential. We looked at one of those yesterday, or Friday. And this one, y equals 1 over x plus 5. We did that last year. That's a rational. Rational, or we could say it's a reciprocal function of x plus 5, just because it's a 1 on top, but either one of those. Okay, so turn over the page. Okay, it says the graphs of several functions are shown. Some of these graphs can be described with a single equation in terms of x, whereas for some it's not possible. Circle the graphs for which it is not possible to describe with a single equation. So back to Math 20, remember you learned about piecewise functions. So you'd be given a graph and you would separate it into its pieces that are defined by a certain equation. But in this case, the first one's a linear equation. So that's obviously we can show with a single equation. Okay, so it says circle the graph for which it is not possible. So I'm not going to circle it. Okay, next one, quadratic. That's back to Math 20. So yep, I can come up with the equation. Doesn't say to do that, so I'm not going to circle that one. Next one, don't know what the equation of that is. What I noticed that this left part here looks like a cubic, and this looks like a linear. So that's something where we might say, okay, f of x equals, and you'd have your cubic here, and your linear, right? And you'd say for which value, so for x less than or equal to 0, for x greater than 0. Right? That piecewise notation for Math 20. Next one, you could use piecewise, but that's also an absolute value function. Anytime it's a V shape that's symmetrical, so if we look at going through the vertex, it's symmetrical about, so that's the absolute value of a linear expression, and then it's obviously translated down. So that we could, so this one I should have circled, sorry. That one we're not going to circle because we can come up with the equation as an absolute value function. Okay. Next one, that one, same thing, you would do it in pieces, so I would circle that. You'd have horizontal, then an absolute value, then a horizontal, or even two linear. Okay. Next one, this is two parts, but recognize it. That's a rational function. Okay, so it'd be some stretch on y equals 1 over x minus 2, because there's going to be an asymptote there. Okay, it wouldn't be y equals, so if I say, oh, you wanted to find it, y equals 1 over x minus 2. That gives me my asymptote, but it doesn't go, for 1 unit over, it doesn't go 1 up, it goes about a half up. So probably this is something like that. You're not asked to do that, so that's okay, but it's probably something like that. Okay, so I'm not going to circle it because I can come up with an equation. Okay, next one. So now we're given a definition for f of x. It's f of x equals x squared. Write each of the following in terms of function. So we're going from the actual quadratic in this case and showing it in function notation. So kind of working backwards to what we did on Friday. So here, if I think about this, this is my answer. If this is what I started with, that means I had to replace x with x minus 3. So this is going to be f of x minus 3. That would give me x minus 3 squared. Okay. So it's sort of the opposite of what we did on Friday. Now we're coming up with a function notation. Okay, next one, this 7x squared minus 2. Well, this is x squared. Okay, so obviously I have to multiply f by 7 and then subtract 2. Because f of x is x squared. Next one, so basically this is your x squared, right? So negative f, but in the brackets there is x plus 1. So in the brackets, it's going to be x plus 1, and then a 4 outside. Common mistake is I will get this from students. There's never a squared or a cubed or anything on a function notation. It's always an f and a bracket, something inside, maybe stuff outside, but that's a common mistake. Okay, and then it says 16x squared in more than one way. Well, the most obvious way, oops, go back to blue, is 16f of x, right? What's another way, a less obvious way? Go back. Yep, f of 4x. Okay, why does that work? Well, if we substitute 4x in for x there, we get 4x all squared. 4 squared is 16. X squared is x squared. Yep. Yeah, just what we mean is just the once. Yeah. Yeah, you could do that, but it gets, we don't need to get that complicated. Yeah. Just one f function. Okay, but in this case, there's more than one way because of quadratics. Right. Okay, now a different function. Now we're going to look at a reciprocal again. So same kind of thing is now write this in terms of h of x. H is the reciprocal. So what is it? It's 3 over x. So if we've got a term of 3 over x, that's pretty straightforward. That's just h of x. And then we're subtracting 5 afterwards. Okay, now the next one is 3 over, but now it's x minus 2. So where there was an x, now there's an x minus 2. So that's basically replacing the original x with x minus 2. Okay, now this is 6 over x. Well, how does that compare to 3? Okay, you would have to, you could go 3 over x plus 3 over x, right, which would be 2 h of x. Or just think about, this is the same as 2 times 3 over x plus 5. So that's going to be 2h of x plus 5. Now D, we've got negative 3 over 2x. So we've got the 3, we've got the x, but we've got a negative in the numerator, 2 in the denominator as a factor. So there's a couple ways you could do this one. Think about it. You could show this right? So negative 1/2 times 3 over x is the same. So that would be negative 1/2 f of x. Okay, or you can think about it as negative 3 over 2x, just kind of pulling the negative out. And that 2x is where x is in the original. So you could go negative, oh, I called it f there, sorry, I should call that h. So here, where there was an x, now there's a 2x. So I would call this negative h of 2x. Okay, so there's more than one way of doing that. Now we're going to review some transformations. So quadratic, y equals x squared, transformed to be y equals negative 3, all x plus 5 all squared plus 12. Well, name the function. You better know it. It's quadratic. And better know what the vertex is. Who can tell me what the vertex is? Back from math point. Yep. Yep, negative 5, 12. So remember, describing transformations, we're going to do a lot of transformations this year, so it's really important to get the terminology correct. So order, so stretches, reflections, and then translations. That's how you write them out. So what do we have here? Well, we have everything. We have vertical stretch, we have a reflection, and 2 translations. Okay, so we've got to say the stretch first. So we say vertical stretch by a factor of 3. And we need to put in about what axis. So vertical stretch are about the x-axis. So you might get a little bit lazy. Sometimes we'll just do abbreviations, but when it comes to a test, when it comes to the diploma exam in January, they want to see all the words, okay? Then reflections next. So reflect, oops, I didn't spell it right. Reflect in, so if you're changing the sign of y, this is going to open down now, before it was opening up. So that's reflected in the x-axis, or in the line y equals 0. And then translations, doesn't matter which order. So horizontal translation. Okay, so take a look at the vertex. It's now negative 5. So that's left 5 units. Okay, because the original vertex was 0, 0. And then vertical translation. Now the vertex is at positive 12, so that's up 12 or up 12 units. Okay. So it says the point negative 2, 4 lies on the graph of the original. Determine its image point. Image point is the new one after the transformations. That's the math word for it. And then verify by substituting into the transformed function. So we want to do these transformations. Okay, so vertical stretch by a factor of 3. I'm going to show the steps. You can do it all in one, but it does say determine, so I should show work there. So vertical stretch by a factor of 3 makes the 4 become a 12. And you could even go here, vertical stretch by 3, just an abbreviation. Reflect in the x-axis, so that's going to make it negative 12. Okay, and then your translations. So left 5, so negative 2 to the left 5 would be negative 7. And then negative 12, up 12 would be 0. So I guess that's left 5, up 12. Okay, so now to algebraically verify. When we verify, don't put it into the whole equation and leave the equal sign there. So I use what's called a T-chart because it looks like a T. And I have my left side and my right side. Okay, don't have to have that, but you have to keep the work separate from each side. So my left side in this is y, right, or is y, and that's my right side. So I'm saying, I'm trying to check y equals 0. So that's what I'm thinking it is. And then my right side is negative 3. Sorry, it's slow because I'm recording. And then x plus 5 all squared. So x is negative 7 plus 5 squared. Okay, and then plus 12. So evaluate that. And I get the left side equals the right side. Okay, so that means it does verify. Okay, so I found the right point. Okay. Now, algebraically determine the x and y intercepts of the transformed function. Verify with a graphing calculator. Okay, so y-intercepts are easy, right? So y-intercept is when x equals 0. So we're going to go y equals negative 3, 0, just forgot again, plus 5. Plus 5, all squared. So that's going to be 25 times negative 3 is negative 75 plus 12. Okay, so that's your y-intercept. X-intercepts, that's when y is 0. Okay, so don't expand out. Remember what we learned in Math 20. You could solve, obviously graphically, we're going to do that afterwards. Algebraically, you can solve by factoring, You can solve by quadratic formula. You can solve by the square root principle. Square root principle is if it's already in this vertex form. Okay, you don't even have to complete the square. So here I would bring this term over to the left. So that's going to be 3 times x plus 5 squared equals 12. Divide by 3, both sides. Then take the square root of both sides and get x by itself. You can expand out and maybe factor, or expand out, use quadratic formula, but it's already, this is pretty straightforward because you can even take the root of 4, right? So x plus 5 is going to be plus or minus 2 because we're taking the square root here, positive or negative. Okay. And so then we'll get x equals negative 5 plus or minus 2. And now actually find those values. Negative 5 plus 2 is negative 3. Negative 5 minus 2 is negative 7. So those are your x-intercepts. Okay, let's just sketch it before we check with our calculator. So based on what we know, crooked. Frozen because recording. Okay, so your sketch should look something like that. Get out your graphing calculator. You can enter that on your own and just check. Okay, so negative 3 bracket x plus 5, close bracket, squared plus 12. If you do a standard screen, you're not going to see the vertex. The standard goes up to 12, but sometimes I start with a standard screen. So standard is 6, and I can't see it, right? I can't see the y-intercept either. So then if I go to window, y min, if I want to see that y-intercept, I've got to be at least as low as negative 63. So maybe I'll go negative 70. Y max, I've got to be at least 12, so maybe I'll go to 15. Okay, we won't need as much for x because of that stretch. If you want to, well, we'll leave it negative 10. I'll leave it like that because we do want to be, so that's pretty decent. Okay. And then you can, if you go trace, it often goes right to the y-intercept, which it does. If you know what if you think the x-intercept, we thought it's negative 3. Sure looks like it is. If I go trace negative 3 and I get 0 for my answer, I know that that's an x-intercept. X-intercepts has y equals 0. If I wasn't sure, then remember you can go second trace, 0, number 2, and cursor to the left of where you think it is, enter, to the right, enter, and enter on that. Okay, or you can graph the x-axis as a function and find the intercept. All of these you'll be using a lot this year, so you need to be really comfortable doing that. Okay, so we've got that. All right, another one. Graph of y equals x squared is transformed to y equals a quarter x squared minus 6. Describe the transformations. Do an image point. So same work as we just did. So I'm going to leave this one for you to do, okay? I don't think there's anything different on that. So you're going to do this. Okay, it's actually a little bit easier than the first one. Okay, now we'll get into something that is part of 30-1 that we've maybe talked about a little bit in 20, but you need to be really comfortable with and know what the definition is. So not that you have to give a definition, but if you're asked to do something in set builder notation, you know what to do. Because last year, I was surprised that students, they got it wrong on the test, and it's like easy marks. Just knowing what form to put something in. So we've used set builder notation before. So all of these with the squiggly brackets is set builder. Now saying that, these really, this one should have X element of the set of reals. All of them should. What happened was, for a while, Alberta Diploma Exam, they didn't have a written response portion to it for a few years. So you would never write the domain or range out. And so we got a little bit nicer, I guess you'd say, and saying that you didn't have to put that. Now we have a written response in the diplomas and they require it. If you don't put XER at the end or YER, then they might take marks off. Okay, so you just want to make sure you have that. But in any case, so this would be Y element of the set of reals. It's kind of like a default setting that it's always reals unless you state something else. But those should be fixed there. In any case, that's set builder because it's using those squiggly set brackets. Interval notation has brackets, but nothing else, just numbers and a comma. Not to be confused with an ordered pair, a point on a graph. So domain and range can also be described using interval notation. A comparison between both is shown using the examples. So if our domain is between 2 and 5, including them, that's our interval notation. So it's usually D with a colon and then that 2 numbers, okay, unless it's infinity. We'll see that in a sec. Notice how there's square brackets here. Notice the difference between this one and this one. So these are almost the same, except this doesn't have an equal sign. These are almost the same, but this one has round brackets, this has square brackets. So it has a note here. In this case, when the domain is expressed in interval notation, it looks exactly like the notation used for coordinates of a point. So you need to be aware of the context of it. So if there's D colon 2, 5, then you know that's domain, and that's interval notation. If you saw D 2, 5, that's likely a point, D 2, 5. So you have to know the context of it. Here, no equal sign, and it's round brackets. Equal sign, and it's square brackets. So the square brackets means you include that value. Round brackets, you get really close to it, but you never touch it. So it would go from 2.02, not including 2, so 2.000001 to 4.9999, right? Never 5, whereas this goes from 2 to 5. So here you have one round bracket and one square bracket. All real numbers goes from negative infinity to positive infinity. Then if you just have one boundary, then you're going from negative infinity here to positive 2. Remember, Pac-Man eats the biggest thing, so the 2 is the biggest. No equal sign, so there's round brackets. With infinity and negative infinity, it's always round brackets. We don't know what the number infinity is, so we can't actually get to it and have a square bracket. So negative infinity or positive infinity, always round brackets. The equal sign gives you the square brackets. If the domain is y less than or equal to 2, so that on a number line, there's 2, there's 5, so that way and this way. then you've got two parts to it. So the word or comma, is now going to be a union symbol, which looks like a U, right? And you're including those, so we've got square brackets. So that's interval notation. So that's something a little bit new, and we'll be using that throughout the course. So examine the comparison table carefully. In interval notation, what is meant by a square bracket? Okay. So square, yeah, so here, it's got a little typed out. Square bracket, this or this, it means it includes I call them boundary values. Okay. Round does not include. Okay, so union is or, one or the other, or both. Okay. Okay, so we're going to practice in the chart there. So complete the following table. So we've got to do one or the other. So the first one, set builder, is given. No equal sign. So, and this is a range, so we go R colon, and no equal sign, so we're going to have round brackets and the boundary values listed. Always in order, lowest to highest. And this is domain. Oops. Messy. So D equals squiggly brackets X. That vertical bar means where or such that. And now we've got the domain X being 8 or greater. So that means X is greater than, not including it because it's a round bracket, it's just greater than 8. And all real numbers. Okay, all real numbers, D colon, from negative infinity to positive infinity. Square brackets includes everything. Range is Y such that, and then I like to put them down in order with a space in between. Range is Y, and then always opening to the right. You've got them in order. Then comma, Y-E-R. Okay, so you finish, I'll give you a minute to finish the rest of those. Okay, so check those. You can use the word or a comma, kind of means the same thing in this last one. And then, given this parabola, we did this one earlier, a couple of minutes ago, but we didn't do domain and range. So for this particular quadratic, in set builder notation, well, remember, For a quadratic, domain is always all real numbers. So in set builder notation, it's x element of set of reals. In interval, then that's negative infinity to positive infinity. Okay. Range, though, remember the vertex was negative 5, 12, and it opened down. So your set builder range will be y less than or equal to 12, set of reals. And for the interval, it's everything less than or equal, less than or equal to 12, yep. So that means it's going to start at negative infinity and end at 12, including it. Okay. So again, look at the context. I have two numbers here, right, that have round brackets, but I don't have D or R next to it. I have V and no colon, no equal sign. So that's representing a point. So this is just to remember. So if a question is given, say a question gives you the domain in set builder and asks you for the range, then you need to give the range in set builder. If it gives you it in interval, then you give it in interval. Okay. So just to be consistent, can't do domain in set builder and range in interval, unless maybe you're asked for that. But you want to be consistent. Okay, so that is the end of the review.